Okay, let's get started. So yeah, we're a little bit late. So yeah, in the last lecture, we continue our discussion on the angle modulation, right? And we first finished talking about introduction, and then we talk a little bit on the property of the angle modulation. So we talk about the constant power property, right? And what's the second property that we covered? Yeah, that's the third, I think. Yeah. The fact is, let me. Oh yeah, exactly. Yeah, very good. Yeah. So yeah, the second one is the fact that this modulation is nonlinear. Yeah, you're totally right. Yeah, the third one is, okay, so what if the system is not linear, right? Then what will happen to the modulated signal, right? Very good. Okay, great. And then, yeah, here is the notation of our discussion. So basically, we denote the modulated signal in this way, and this theta entire thing, so that will carry the information, right? So in practice, so the theta will consist of a carrier and the information signal, okay? And so the relation between the phase and or the angle and the frequency is the derivative of the angle. You'll get the frequency. You'll get the frequency, right? And in practice, or in our modulation, so normally this will be a function of time as well, right? That's how it carries information, right? So then we denote this frequency as a function of time, and we use I to indicate. So that is instantaneous frequency, okay? And then for that, there are two kinds of angle modulation. So one is PM, the other one is FM. Here, the focus is FM, right? So we're going to talk a lot about FM. So when we talk about digital communication, then we're going to talk about PM, right? Because that is mainly used for digital communication. Okay, and so here are the general definition for the PM. So basically, the reason it's called the phase modulation, it means that the phase will carry the information. Phase is the angle here, right? The angle, or this is also called phase, right? But here, the phase basically means this part, right? So basically, this is a carrier frequency, and then we add the variation part, so represent information. And so this is a linear function of the input signal, right? So that's very important. And this constant factor is called phase sensitivity. Okay, and then there's some unit here going on, and you can see that. And the entire modulated signal looks like this, right? The carrier frequency plus the phase part that carries the information. Okay, and yeah, miss symbol here, right? So this should be d theta, and that is so if we do a derivative of the entire phase, here should be theta t, right? And then you get the carrier frequency, and then the sensitivity factor multiply the derivative of the message signal, okay? And so basically, that's the instantaneous frequency. So so that's in radians. If in hertz, so you need to divide everything by 2 pi to get it, okay? And for the frequency modulation, so basically, what you do here is that the frequency variance, so this guy represents the message, right, the information. So that equals to carrier frequency plus the message part, right? Again, so this FM basically means that the instantaneous frequency varies linearly with the message signal, m of t, right? And here the k is the sensitivity factor of the frequency, right? And so this is, again, this is in radian. And if in hertz, you need to divide everything by 2 pi, okay? So now we can characterize the relation between the frequency and the phase, right? So as we said, right, the frequency is the derivative of the phase. Therefore, the phase would be the integral of the frequency, okay? And here is how you compute it. So integral all the frequency, and you get the phase. And if for FM, so it will be like this, right? So this is basically carrier frequency, and then the message, and integral that to get the phase part, okay? So yeah, that's very nice. And so this is a modulated signal. You can see, so the cosine, I mean the carrier is here, and then we have a factor in front of it. And then we have the carrier frequency, and this is the frequency, right? So from this formula, you can see, okay, it depends on, in practice, what you do, right? If it's, if it's more easier to generate the frequency, then you're going to generate the frequency first and then do the integral, right? So to get the phase, right? So Or if it's generate the phase, it's easier. Then you need to do the integral first to get the phase and then put that here, right? So very, very nice. Okay, and in general, so that's the general angle modulation. So basically, in general, can write something like that. So we pass the signal through a system called h of t, right? And then do the integral, so get the phase part, and then you can see this kind of thing, right? And the PM and FM are two special cases of it. For the PM, so this system impulse response is just a Kp multiplied delta. And for FM, it's just a constant, right? Because for FM, you just use that times a constant, so h of t is a constant. Okay, so that's basically the generalized angle modulation. And for the property, so we discussed three. So one is the power is a constant. Right here, when you consider the case when the frequency of the signal is much smaller than the carrier frequency, right? Then within one period of the cosine, we can see that it as a constant magnitude, right? Then we can compute the power, which is almost a constant. And so that's the advantage of angle modulation. And then we see angle modulation is a nonlinear modulation, so which is not good, right? We want everything to be linear, right? This is nonlinear, so then we need more complex system to do the modulation and demodulation. Okay, so we're going to see that later. And then we'll talk about the effect of nonlinearities, right? So yeah, we didn't finish that part, right? So let's continue from there. So basically, what we have seen in the last lecture is that for the DSBSC, so we can see the nonlinearity have a negative impact, right? So now we'll see whether for FM we still have this negative impact or not. Okay, so let's see what we're going to cover today. Today is our lecture 19. We have, let's see, so basically we're still talking about angle modulation. And the first part we're talking today is the properties of angle modulation. And basically, we're going to talk about the nonlinearity of the signal, right? And then we're going to talk about modulation for FM. Okay, and we're going to see how well we can go. So next topic is demodulation. But we're not going to talk about demodulation today, right? Just to give you a heads up. So that is what we're going to talk about. Okay. Yeah, in the modulation and the demodulation, so we're going to talk significantly on this PLL, the phase-locked loop. So that's a very important concept in our class. Okay, so let's talk about topic one, that is nonlinearity. Impact of the signal, right? So basically, we talk about the SDSB, SC, right? So if that equals to this guy, and then when the nonlinearity impact is that when the output signal is this mt cosine omega ct plus, I think I have a constant here, a and b. So this is cube cosine cube. Okay, and then after some manipulation, so what we're going to get is as follows. So this equals to a times mt cosine omega ct and plus 3 over 4 bm cubed t times cosine omega ct, and then we add 1 over 4 bmt cube cosine 3 omega ct. Okay, yeah, that is, let's see that done. Yeah, that is basically what we have here. Okay, very good. Yeah, now how we compute it is that we take a cosine out from here and here, right? And then we have a cosine square here. We expand the cosine square by 1/2, multiply 1 plus cosine 2 omega ct, right? And then there's a 2 omega ct, and there's a 1 omega ct here, and then we combine those two using the trig identity. So if you forgot, yeah, we had some confusion there last time, if you still remember, right? So yeah, just go over the lecture notes and see how we can get it, right? So yeah, just some algebra going on here. Okay, and then, so the thing we want to emphasize here is that, so basically, we have something that is really bad, right? For this part, it doesn't matter, right? So this part, so that can be filtered out, right? We can filter it out, right? Because it's high frequency, it doesn't matter, right? So what matters here is basically this, right? We have some nonlinear impact here. So the magnitude now, let's say if we use an envelope detector here, right? So basically, this part will negatively impact the envelope here, right? So it will not be very good. Oh yeah, we don't have this, right? So we take this out here. So that is not very good. Yeah, is that clear on this part? Okay, great. Okay, yeah, let's see for FM. Okay, so for FM, let's see what we're going to do, right? So let's recall the S, FM, the modulated signal, look like this. Cosine omega ct plus, we have an integral of the instantaneous frequency, right? So we denote that as psi t here, right? And so this is nothing but this. Right, so this is basically the frequency modulated signal, right? Yeah, use the AC here. Okay, so now let's do the same thing as there, right? So basically, what the system does is that to the input signal, the output is to use A multiply S plus B S cube, right? So now let's do the same thing here. The output, let's see, the output is called YFMT. So that is A times this guy, and B plus B times FMT cube, right? Right, let's see. So what will happen on this guy, right? If we have this kind of nonlinear operation. Okay, so we plug everything in here. So we just keep this phi t to make things easy. So basically, this will equals to small a times AC times cosine omega c plus this guy, right? And then we add b this thing cube, right? AC cube cosine cube. Okay. And next, we're going to do something very similar to this, right? So basically, we have a cosine here, and we have cosine here. Then we take these two cosine out, right? So that basically equals to the follows. So let's see what we got. So we take this cosine out. So basically, we have AC, small a times AC, and add b AC cube, cosine cube, right? The entire thing, like cosine omega c t. So here should be a square. Right? And then we're going to do exactly what we're doing for the DSBSC case. Okay? So basically, here we have a cosine square, right? So the cosine square will equals to what? 1/2, 1 plus cosine 2 omega ct. Right? So basically, we're going to plug that in and see what we get. So basically, here is AC plus half B, and times AC cube plus half B plus AC times AC cube times cosine 2 omega CT, right? And then the entire thing multiply cosine omega CT. Yeah.
What happened to the phase shift?
Oh, I forgot, right? So yeah, very good. We need to. Yeah, that is very important, right? Because that carries information, so we need to add it everywhere. Very good. Phase shift, phase shift. Yeah, let's see, is that right? Okay. Yeah, 2, right? Yeah, maybe I'll write them together to, let's see, this should be 2. What's that? Then we multiply that. Cosine omega CT plus phi t. All right? Yeah, check it. You have our first term, and then add the second term, this guy multiply half, and then multiply this guy. So we have, oh yeah, yeah, that is correct, right? Multiply half. Yeah, that is correct. BAC cube plus half BAC cube multiply this guy, and then entire thing multiply whatever outside. Is that right? Yeah. Okay, you can see this is exactly the same as that.
That cosine is supposed to be 2 omega CT plus 2.
Oh yeah, you're right. Definitely. Very nice. Yeah, if you can see the mistake here, so basically it means that you are also computing, right? Which is excellent. Here, right. All right. Yeah, I don't have those in my notes, so I just give steps. So it's very, it's not that easy to compute everything, online, right? Okay, let's continue, right? So now we have very similar to that one, right? So we have this term and this term, okay? So we're going to use trig identity to combine those two, right? Cosine multiplied cosine equals to what? Right, so now basically what I will do is to compute this term, multiply this term, right? So for those two guys, this multiply that is okay, good, right? We need to use this multiply this, okay? We have cosine times cosine, right? What is cosine times cosine? Yeah, let me make sure it's.
Isn't it cosine of the angle plus the other angle times the cosine of the angle minus the
Exactly. Yeah, so basically the only thing we need to remember here is, so it's cosine plus cosine or cosine plus sine or sine plus sine and whatever, right? So cosine times cosine equal to cosine plus cosine, right? So basically, yeah, I'll write in this color. So for this guy, yeah, I'll just do this, right? So for this two, this multiply that. So this equals to cosine. We have half in front. This minus that, right? If we use this minus that, we have omega CT plus phi CT, right? And then plus half this plus that, right? So that is 3 omega CT plus 3 phi psi t, right? Yeah, that's how it works. And you can see that. So if this multiply that, we have additional term here, right? For these two guys, yeah, we have this kind of thing already, right? So we need to use this to multiply this first, right? That's A small a times big AC plus half this thing plus cosine omega ct plus phi t, right? And then from here, we get additional this term, right? We need to use this plus that. So that is the 1/4 BAC cubed cosine omega ct plus phi t, right? And lastly, we have this, right? This multiply this. So that is half BAC cubed, and then cosine this guy, right? 1/4. We have 1/2 here. We have another 1/2 there. So this should be 1/4 cosine 3 omega ct plus 3 psi t. Okay, very good. And then we'll combine this and that, right? So basically that equals to small a c add. So we need to add this and this constant, right? 1/2 plus 1/4 is 3/4 BAC cubed, right? Together times cosine omega ct plus phi t, psi t. And then add the last term, right? So 1/4 BAC cubed cosine 3 omega ct plus psi t, right? So that's finally what we got. Okay. Yeah, looks good. Okay, so now let's see. So this part doesn't matter, right? As what we said before, we have 3 omega c here, so that will be filtered out by some low-pass filter, right? Doesn't matter. So now let's see for this part, right? Remember, so this is the message, right? So does it matter? Does the nonlinearity matter? Right, remember, so what do we say here? Okay, it does matter for DSBSC is that we have this kind of term. If we do an envelope detector, so we have this at that. So that's now equals to, this at that doesn't equals to some constant multiply MT, right? So it is a problem here, right? But is this a problem here? Is it a problem here? It's not, right? So this is a constant. Right, just another, we can write that, use another constant, A prime, to represent that guy. And then we have still our original message here, right? If the detector, if we use some kind of demodulation, so any demodulation works for, just a constant or work for this guy, right? So it doesn't matter, right? So this is one advantage of the FM signal, right? So this kind of non-linearity of the system doesn't matter for this. Yeah.
How non-linear is like regular air channel? Like if you're doing like communications, how
Very
much
good.
does that non-linear?
Yes, very good question. Yeah, the channel, almost nothing. Yeah, the big thing for the channel over the air is the change. So normally the system is not linear time invariant system. It's a linear time varying system. The linear part still holds, but it's normally time varying. Depends on how big the change is. This is one reason that we're using digital communication. So digital communication is more robust to this kind of thing, right? But the nonlinearity came from the power amplifier, not from the air. Yeah, normally for any power amplifier, there's some kind of nonlinearity. So this is very important. So we see this kind of thing all the time, based on my knowledge. Yeah, because I did a project before, to use the machine learning approach to solve the power amplifier nonlinearity problem. Yeah, so I know definitely there's something going on there. Yeah, good question. But over the air, I don't think so. Over the air, there's not much nonlinearity. And also, I think for the optical fiber communication, there's some nonlinear linearity going on for the the optical fiber. Yeah. Yeah, I remember I did study some kind of this problem very long time ago. I remember there's some nonlinearity for the, I think still coming from the power, right? If you increase the power in the optical fiber a lot, I think there's some nonlinearity, shows in the channel. Okay, great. Any other questions? Okay, so we're good on this, and then we're gonna see the next thing, the next property. Okay. Okay, so now basically what we have seen so far is that there's some advantage in terms of the nonlinearity of the FM, right? So it's very good in this case, but what do we lose, right? One thing is that the modulation itself is nonlinear, so that's not very good, okay? But later on you're going to see it's not a big problem. Okay, we can do that. But what else? Right? Is there any other problem for this kind of modulation? Right? So normally, what kind of property we talk about a signal? Right? We talk about is whether it's a linear or nonlinear, right? And what else we talk about the signal? Right here, everything's in the time domain yet. So we didn't talk anything about this in the frequency domain, right? So now we're going to look at this signal in the frequency domain to take a look, right? You may imagine a little bit, right? So yeah, for this kind of signal, right, in the frequency domain, what's that look like? Right? Can you guess? You know what we're going to talk something about bandwidth. Okay, of the signal. Right? For the DSP-SC, it's very clear about the bandwidth, right? It's just bandwidth of the signal, and if we move it, we double it. Right? If it's not SSB, right? That's it. Right, how about for this one? Right? What is the bandwidth look like exactly in the frequency? I'll take a guess. Yeah, probably not going to be good, right? Yeah, because we gain something, normally we lose something, right? There's trade-off everywhere. It's very, very rarely seen that we gain on this aspect, we gain on the others as well, right? I'll take a guess. What will be the bandwidth of this system?
Is it just like the maximum of the message signal?
Very good. Yeah, it's almost. But that's not exactly. Yeah, that is what we use in the practice. Intuitively, that should be the one, right? What is the maximum value of the message? Should be the maximum value of the bandwidth, right? So yeah, sort of. Yeah, that is what we use in practice to approximate the bandwidth. But the exact bandwidth is not like that. Oh, by the way, there's a big theorem on that as well. So we're going to talk about, which is not that trivial. Okay, anyway, yeah, let me introduce it. So basically, let's analyze the bandwidth of this kind of signal, right? So because we're going to analyze the bandwidth, so we have to look at the signal in the frequency domain, right, instead of time. Okay, so now let's see. So let's have some notation here. Yeah, I'll introduce you some new notation. So basically, let's denote A of t equals to this guy. No, from 0 to t. From 0 to t, mt dt. Oh, no. Yeah. Yeah, I think I talked too much. Yeah. How come when, if I read something it's not correct? Yeah, it means that I have no idea what am I talking, right? So that's very bad. Okay, yeah, let's continue. So I have this notation to make our life easier. So basically, now what I'm going to do is as follows. Okay, so yeah, for this guy, yeah, remove it, right? So for our FM signal, it's just a cosine, right? We can definitely do the Fourier transform directly on that, right? Not a big deal on that. But instead of doing this, we're going to do something different, right? So you'll see that we're going to do this kind of analysis a lot, right? So normally what we do is that we're going to do analysis on the complex exponential of this kind of, a complex exponential version of the cosine. So which basically means that if we take a real part of the complex exponential, it will give you the cosine, right? Does that make sense? Let me write it down and see whether it makes sense or not. The only reason that we're doing this is that for the complex exponential, it's very easy to see the Taylor expansion. Okay, so if we see the cosine, Taylor expansion is still doable, can still do that without any problem. but it missed some terms in between, right? So which is kind of ugly. So yeah, we just do the complex exponential version, and then we take the real, right, and see the property. Okay, so basically we denote the signal as fm hat, right? That is the complex exponential. You also use the constant AC here, so that is a complex exponential. And here is j times omega c t plus kf, so that is the frequency sensitivity. Multiply this guy, right? Because that's frequency modulation. So yeah, we'll only talk about the frequency modulation here, right? We don't talk about the phase now. AT, right? So that's the complex exponential version of that, right? So we can imagine that if we t, so if we take the real value of this guy, we take the real of this guy, okay, and then you'll get the original FM signal, right? Okay, and then we're going to do a Taylor expansion on that, right? That's why we're doing this. So remember the Taylor expansion on this EX. So EX is very nice, right? So we have only one formula for Taylor expansion on everywhere. So that equals to what? A summation n from 0 to infinity. We have xn divided by n factorial. So that's the Taylor expansion, right? So this basically equals to what? The first term is just 1, right? Because n equals to 0. And second term is x. And third term, so it's x divided by 1 factorial, right? It's x. Then it's x squared divided by 2 factorial and so on, right? So that's basically how it looks like, right? It has all the terms, right? That's kind of nice. So okay, so now basically we're going to do the Taylor expansion on this and see how it looks like, right? So basically for this guy, we can break these two terms. So basically that equals to what? AC, E, J, K, F, A, T, and then multiply the carrier, E, J, omega, C, T, right? So by the way, I think this is the first time you see this kind of analysis, right? But so this is what we're doing today, okay? So we never do this analysis over cosine or whatever. We do everything in this form. So you will see when we talk about the digital communication, so that's the form that we're talking about, right? The reason we can use complex exponential is that we're using QAM everywhere, right? QAM is, we can show that it's equivalently to transmit a complex number over the air. Okay, yeah, that is what we are doing now today. Okay, yeah, we never do the analysis on the cosine directly, so that's too complicated. Yeah, we don't like the trigonometric signals, although we use that. Okay, anyway, so yeah, this is what we got, and then now let's take we're going to use the Taylor theories on this. Not this, okay, just on this. For now. Okay, let's see what we're going to get. Okay, so we say this equals 2. So this sign is the equal sign is following here, right? So this is on the other side. So basically, we have a constant in front, and then we have our Taylor expansion, right? So for that guy, we need to be a little bit more careful on this j here, right? Because this j, you'll see why it's important, because this j squared equals to -1 is not complex anymore, right? So we need to deal with that a little bit more careful here. So basically we have 1 plus x, right? X, which is whatever inside here. KF, AT, right? Okay, and then we add j square, kf square, at square, everything square, and then divide by 2. Yeah, 2 factorial is 2, right? Okay, and then we plug the cube 1, j cube, kf cube, at cube divided by 3 factorial. Yeah, that should be 6 and so on. Okay, so this is the Taylor expansion part, and then we multiply this by the last part, right? So for this EJC omega, so we don't do Taylor expansion on that, because if we do that, it will be very complicated, right? So what we do here is that we're going to expand this using the Euler's formula. Okay, so that equals to cosine omega ct plus j sine omega ct, right? Yeah, hopefully you'll see where am I getting, right? So, okay, yeah, because we're going to take the real part of this signal to get S of Fm, right? This is the signal that we're interested in. The only reason we're using that is we can easily do this kind of expansion, okay? So after this, so let's see what will be left. What will be left? God. If we take the real part of it, right? So that equals to real part of the SFM hat t, right? And it will be the real part of this guy, right? So let's see the first term, right? We'll have this number of terms here, okay? So let's see the first term. The first term is the AC multiply 1, right? And then multiply this guy, right? Cosine. Yeah, this is a little bit messy, so just follow me closely. Yeah, let's take the AC out, right? Doesn't matter for this one. Okay, so this is the first term. Okay, so how about second term? So second term is that we have this guy, right? And then again multiply this guy, right? So it's still there. So let's write it down. Oh no, take the real part, right? So this is clearly this is the imaginary part, right? Well, j here. So this guy multiply this guy is still imaginary, so it's gone, right? We don't have it. Then let's see this guy. So after checking about cosine, we check about sine, right? Okay. Oh wait. So for this guy, so this guy multiply cosine, it is imaginary. But this guy multiply sine, it becomes real again, right? So I have a j here, we have j here, j squared is -1, so we need to be careful. Right, I have -1 here, so that's kf times at times sine omega ct, right? So we have this term left. All right, and then let's continue doing this. So now we need to check this term, right? So j squared equals to -1, right? So this is real. So this is real, then this multiply cosine will stay, and this guy multiply sine will go away, right? Then we have a minus here, right? So we minus, yes, minus kf squared at squared over 2 multiply cosine omega t, and so on, right? So you can do this for all terms here, right? The reason I'm stopping is that so now we're at frequency about omega c, right? So if you not frequency at omega c, so we're at this this magnitude at a squared here, right? For the other term, you're going to see a cube, right, and a fourth, and so on. Okay, so yeah, you can get all those terms, right? And from this expression, we can see two things. The first thing we can see from here is that, so we have an AC multiply cosine here, right? What is that? Do you see AC multiply cosine anywhere? The SBSC. Oh no, sorry, no SC, right? AM, right? We multiply. This is a carrier, right? So this is the carrier. Okay, very good. How about this? Do you see this kind of thing anywhere? Right? This. Wow. Yeah, my writing is so bad. Yeah. So this is AT, right? So. Yeah, this is AT, right? Do you see this anywhere? Constant, multiply message, multiply sine. If it's a cosine, are we good? Yeah.
Is that the original signal like out of phase?
Say again.
Is that the transmitted signal out of phase?
Transmit signal what?
Wait, no.
Yeah. Oh, by the way, for AT, we need to remember what that is, right? That's the integral of the original signal, right? But it doesn't matter. Just assume AT as the transmitted signal, because if we get AT, we do a derivative, we can get the message, right? Assuming that we can do derivative, which is easy, so we can do derivative using some circuits. Okay, we can even do a derivative using the phase lock loop. That we're gonna see how we can do that. So derivative is fine. So basically, I'll just call that. See whether it makes sense or not. So this is like the DSB SC component, right? So sign is just a phase shift, right? Let's say if we can figure out the phase, it doesn't matter anymore, right? So that's the DSB SC, right? Let's say if we have this and that, then we can use the envelope detector to detect the signal. It's AM. Does that make sense? Sort of, right? Yeah. So just make sure I understand, okay, so this part is okay, and this part is okay. Okay, to demodulation, although we didn't talk about the demodulation and the modulation yet, right? And you may imagine, right, let's say, so if the KF times A, so this number is not big, it's small, less than 1, for example. And then once the square here, it will become smaller. And the cube, force, will become smaller and smaller. And then everything here later on can be ignored because they are so small. Eventually, what we are transmitting here is this plus that. What's that? That's modulation, right? So that's how we do modulation. If KF times A is small. If it's big, we cannot do this. But if small, so this add that is our modulation. That makes sense? Yeah, so basically, when we talk about the modulation, we're going to repeat it. So hopefully you still remember. This is number 1 we can see from this formula. What is number 2? Bandwidth, right? So given this, can you tell me the bandwidth? Yeah, you can, right? So the bandwidth will be equal to the bandwidth of all the terms here, right? Not add them together. It's just like union them together, right? So let me see. So yeah, for this guy, right, for this AC here, so what's the bandwidth of AC? Yeah, let's assume the bandwidth of AC is B, capital B. The bandwidth of AT is of AT. So that is capital B. Okay. So if the bandwidth of AT is capital B, then the bandwidth of this guy is just 2B. Yeah, let me see how I want to say it. If I want to say, where am I getting, right? So yeah, let's ignore this sign at this moment, right? Just take a look at AT here. So if AT is B, then the bandwidth of AT is just B, right? So what's the bandwidth? Yeah, let me use another color. So what's the bandwidth of A squared? So what's the bandwidth of that? Yeah? 2B, right? Because so in the frequency, so it's AF, the frequency signal, convolutes AF, right? The bandwidth will be doubled, right? So what is A cube? Right? Later that we didn't write. What's the bandwidth of A cube? We do the convolution again, right? That will be 3B, right? And what's the bandwidth of AT power n? NB. Right, you get it? So basically, every time when we do the convolution, we just add the additional bandwidth onto it, right? So look at here. So for the series expansion, n is from 0 to infinity, right? It basically means that n will go to infinity, right? So n will go to infinity. So basically, it tells you that the bandwidth, the band bandwidth of SFM. So that all goes to infinity. Okay. So that's the bandwidth of FM signal. Okay. So precisely speaking, it's infinity. Yeah, of course, probably will have a very small component in the high frequency component that we're going to ignore, right? So it doesn't matter anymore. Let's say if this component is very small, then we can ignore from here and so on, right? Of course, in practice, bandwidth is not going to be infinity. The important bandwidth at least. So, okay, very good. Okay, I'll talk additional 3 more minutes and then we stop. Okay, so that's very easy to talk. The next topic. So this is the last property of the FM, of the angle modulation. So next, we're going to talk about modulation. How we can do the modulation? So for modulation, two. Yeah, so basically it didn't miss anything. I covered that already. I'm going to talk about that, right? Yeah, for modulation. So we have a special term for it. We call that narrow band FM. By narrow band, it basically means that the bandwidth of the signal is small, right? Or, so in the communication system, you always see narrow band, broadband. Basically, narrow band means that in the frequency domain, it's very small, almost one frequency component, point, sorry, right? When you see a wide band, or in other words, when you say narrow band, it basically means the channel doesn't change, actually, in the current digital system, right? Because when the band is very small, the channel doesn't change a lot. Okay, when you say wider band, we need to deal with the changing of the channel. But basically, narrow band means the bandwidth small. Wide band means bandwidth large. Okay, by narrow band, right? Basically, this means exactly the bandwidth of signal is small, or in other words, it exactly means that this guy is small. Okay, so when this guy is small, then you can see you can ignore all the higher frequency components. So our signal is a narrow band signal, right? So that's how we do the modulation, exactly that. So basically, let me write it down. So there's an example of it, NOAA weather station. So that use this kind of modulation. So we say our assumption here is that if KF multiply AT, so that is much smaller than 1, right? Then the higher order term will go to 0 very fast, right? In this case, our modulated signal FM, so we can approximate that only use the first 2 terms, right? Which is AC times the cosine omega CT. So that's the carrier. And then minus KF AT times sine omega CT, right? That's it. Because all the other terms will be ignored. Okay. And again, so I want to emphasize this guy a little bit. So this is almost a DSB-SC, right? This is also almost a DSB SC, right? If I add that, it will not, there's no SC anymore. But only this term is a DSB-SC with 90-degree phase shift, or 90-degree, or pi half phase shift, right? Because we have a cosine instead of the sine, okay? And in this case, so for the entire signal, can you tell me, let's say if the bandwidth of AT is B, right? And then for the entire signal, can you tell me what's the bandwidth of this guy? What's the bandwidth? It will be same as the DSB-SC, right? Right, that would be 2B, right? Because we shift it. Okay, it's not SSB, right? It's just DSB, double sideband. So same as that. Okay, so I will draw a diagram and then we're done. Okay, I just want to draw this diagram to show the modulation diagram. Yeah, the modulation diagram is as follows. So first, we need to get our AT, right? So our input is empty. How to get our AT is to do an integral, right? To do an integral, and then here we get our AT, right? And after that, remember, AT is, I remove it, right? Yeah, AT is the integral of our MT. Just remember that notation-wise. And then after that, it will be our DSBSC signal, right? So here, we need to multiply KF here, right, to get our KF AT, right? Then after that, we just win that through a DSBSC modulator, okay, DSBSC modulator. The only difference here is that, so here we generate, normally what we generated here is a cosine, omega CT, right? So, but here we say we need to get a sine, right? So we shift this by 90 degree, pi half, and then we use that to modulate DSBSC, okay? And then we add that together. The output signal here, yeah, we have a constant AC here. And then here is a minus, here a plus, right? And then, yeah, we get our SFM signal out, right? So this is the modulation, okay, for narrowband FM. Okay, so in the next lecture, we're going to talk about general or wideband, okay, and see how we can modulate. In that case, we can now ignore the higher frequency component anymore. Okay, we need to deal with every term. Let's see how we can do that. Okay, thank you. Yeah, sorry for the late today.